All right, homework number 18. This follows day 2 of our alternating series notes. The first section just says determine the convergence or divergence of the series. So as soon as I see a -1 to a power, I'm thinking of running through the alternating series test. So this series is alternating because it's got -1 to the n plus 1, which will go back and forth between even and odd powers of n, or of -1, I mean. And the next thing is to check that the terms are approaching 0. So the limit as n approaches infinity of n squared over n squared plus 4. We're looking at this in absolute value. This is not equal to 0. This is equal to 1. So I'm going to stop there and say that this series diverges. It's not by alternating series test. It's by nth term test. Even with the alternating piece left in, even if you left that in, this series would ultimately end up with like +1 -1, +1 -1. So you're never going to get to adding 0 in the end. All right, for the next problem. Now, normally we say, sine and cosine are not alternating series necessarily, but this does have, it's not just sine of n, it's a sine of 2n minus 1. So you can check this if you want. This says starting with 1. If I plug 1 into this, and this whole thing is in the sine function, I would get sine of pi over 2, and that's 1. And if I plug in 2, I would get the sine of 4 minus 1, 3 pi over 2, and that's -1. And if you keep going, it is going to alternate. The sine of, if I put 3 in, I get 5 pi over 2. That gives you a full 2 pi plus an extra half, so that's the same as sine of pi over 2. So this is alternating. And the next thing to check is the limits as n approaches infinity of the sine of 2n minus 1 over 2 times pi. All right, so as n approaches infinity, we're kind of running into the same thing again, right? Are these terms approaching 0? No, it's just going to keep bouncing back and forth because there's nothing else. Like if this were like over n or something, then sure, but this is equal to plus or minus 1. So this also diverges by nth term test. In order for the alternating series test to apply, the terms have to be alternating but approaching 0. So we want this to be happening, not just bouncing back and forth between two extremes. All right, same idea for this one, cosine of n times pi. Yes, those terms are alternating because the cosine of pi equals -1. The cosine of 2 pi equals 1. Cosine of 3 pi equals -1. So yes, it's alternating, but the limit as n approaches infinity of the cosine of n pi is just going to keep going back and forth between plus and minus 1. All right, so this also diverges by nth term test. All right, use theorem 9.15 to determine the number of terms required to approximate the sum of the series with an error of less than 0.001. Now, I'm going to show you both ways to do this. Most of these are calculator problems, but I have seen them on the non-calculator part of the test too, so it's good to prep for both. All right, so what do we do if this is non-calc? First of all, set up the problem. They're telling us the error, which is the absolute value of the difference between the actual sum and our partial sum. It's equal to the absolute value of the remainder of that partial sum, which is always less than or equal to the absolute value of the n plus 1 term, the first neglected term, the one that you're going to leave off. And we want that to stay less than 0.001. Okay, now working here. The absolute value means we ignore the -1 to the n plus 1. So this is 1 over n plus 1 squared. And let's change this decimal to 1 over 1,000. They usually will give us, on a non-calculator problem, they'll give us this as a fraction anyway. Really, that just means we're looking for 1,000 to be less than n plus 1 squared. Now, because I can't just nicely square root 1,000, I'm just going to do a little bit of like plug and chug over here. So think about some numbers that you know squares of. Like, for example, 15 squared is only 225, so I've got to go higher than that. So 20 squared is 400. 30 squared is a good spot to start, right? 30 squared I know is 900, so that gets me pretty close to 1,000. What's 31 squared? I'm not quite sure. I do know it's already bigger than 1,000, so I could just say I know this is going to be 31, but sometimes later in this chapter, they will have us calculating some of these values. So, oh wait, what did I just do? 1, 3. Oh yeah, see, this is just short. So 31 squared is not good. It's good that I can calculate that, right? Let's see if did I do that right? 3, 0, 3, 9. Yeah, we're only at 961. So maybe it's 32 squared. What's 32 times 32? Let's see. 4, 6, placeholder, 6, 9. There it is. 32 squared is 1,024. So I know that n plus 1 needs to equal 32. That means that I would need to use 31 terms in order to get this accuracy of an error less than 0.001. All right. What if I'm allowed to just use a calculator? So I can do the same calculations I just did using a calculator. Or I like to type in like 1 over x plus 1 squared. And then I hop over to my table. Now my table is starting at 0. And I could just scroll down until I get to 30. Or you can jump around the table. If you go to second window, you can tell it where to start. So I was guessing 30 before. So 30 gets me, this is still more than 0.001. Make sure you're in this column to see this. 31 is 0.0009765. So that is correct. 31 is the correct answer because that is, we're not rounding this ever. So that is less than 0.001. All right. And then that's all we had to do with that. For the next set of directions, it says determine whether the series converges conditionally or absolutely, or does it diverge? So I've kind of split this into 3 steps, and I'm really going above and beyond with my writing here, but I will show you if this is free response, which it could be, what you would need to do. So first thing you're investigating is, does this converge in general? So this is alternating. So I'm going to apply the alternating series test. The terms are alternating. Take the limit as n approaches infinity of the square root of n over n cubed. That's bottom heavy. You could also simplify that. That's 1/2 minus 3. That's 1 over n to the 5/2. But that's 0, so that's good. And then we're supposed to sort of confirm that are the terms decreasing. So if you plug n plus 1 in, is that a smaller fraction than square root of n over n plus 1 cubed? Oops, this is supposed to say cubed. I'm going to say yes. The reason I don't worry too much about this or doing the math on this is because I've already shown that the terms are decreasing towards 0, right? So yeah, they're decreasing. So I just kind of write this down just to cover my tracks, but really they're mostly looking for that limit. Anyway, so this series, I just want to be specific about which ones I'm talking about. So you might not always have to rewrite this, but I think it's good practice. This series converges by the alternating series test. And yesterday's homework just stopped there. But when they say determine whether this converges conditionally or absolutely, so now that I know it converges, the second thing to do is it only converging because it's alternating, or would it converge without the alternating piece? So this is what you have to write for a free response if you're doing this. You have to write the full formal series without the alternating piece. So write this down. It's not enough to just get into your conclusion. It's not enough to just write the expression without the summation. You have to write the whole thing with its bounds. Boom, write that down. If you would like to simplify it, you can. That is optional. If I subtract 1/2 minus 3, 1/2 minus 6 over 2 is n to the negative 5 over 2. So you're getting n to the 5 over 2 in your denominator. So this converges by p-series test. Again, if you write this without the summation, which is the most common thing I see when I grade these free response questions, you're not getting credit for that section when it could have been so easy. Just don't be lazy about writing your summation. What's your conclusion then? This series converged when it was alternating, and it converged when it was not alternating. So this series, the original series that's alternating that they're asking me about, converges absolutely. Meaning no matter that it's alternating or not alternating, it converges all the time. All right, take a look at 55. So I'm going to do the same thing. So the first thing is to apply the alternating series test to verify that it converges in general. So these terms are alternating. The limit as n approaches infinity of 1 over n plus 3 cubed is equal to 0. That's squared, is equal to 0. That's a bottom-heavy function. And it's fair to say that if you plug m plus 1 in, so you get m plus 4 squared, that is less than 1 over n plus 3 squared. So the terms are definitely decreasing, and they're decreasing towards 0. So this original series converges by alternating series test. Now that you know that, you're checking for absolute or conditional. So again, you have to rewrite the positive series. So the series from 1 to infinity of just 1 over n plus 3 squared. Now that's not a true p-series, so I'm going to use a comparison test. You could also do integral test, but why do integral if you can just avoid that? So I'm going to compare 1 over n plus 3 squared to 1 over n squared. The first fraction is smaller. Okay, and what is it that we know? Again, you have to write this whole series, the series from 1 to infinity of 1 over n squared. So don't just write 1 over n squared, and don't just write a sigma without the notation. That is a convergent p-series. So this series converges when it alternates. It converges when it doesn't alternate. So again, the original series, that alternating one, converges absolutely. Now, I'm writing everything out just to make sure that it's crystal clear what we're referencing when we're talking about all of this. I think on the AP test, you could get away with just converges absolutely without rewriting the series. But if you want to be safe, this is a nice, thorough way to do it. All right, let's look at 58. Does it converge in general? Well, this is alternating. The limit as n approaches infinity of 1 over n radical n, that's bottom heavy, so that goes to 0. And it's reasonable to say that 1 over n plus 1 times radical n plus 1 is smaller than just 1 over n radical n. All right, so this series converges by alternating series test. Now that I know it converges, I want to look at the non-alternating. Excuse me. So I want to look at the series of 1 over n radical n is the same as n to the, if I add those exponents, 3 halves, right? 1 plus 1 half. This is a convergent p series because p is greater than 1. So again, that means that this original series converges absolutely. I'm not sure why I picked so many examples that are absolute, but we will get one that's conditional in here somewhere. All right, take a look at this one. Alternating. Yes, negative 1 to the n. The limit as n approaches infinity of n over n cubed minus 5. This is bottom heavy, so that limit is 0. And I think it's reasonable to compare n plus 1 over n plus 1 cubed minus 5 to say that's smaller than n over n cubed minus 5. Because remember, if you cube this out, you're going to get a few extra terms that involve an n. And the top, n plus 1 versus n, is not much different at infinity. But n cubed plus 3n squared plus another 3n squared, or whatever it is, a 3n plus 1, that is going to be much smaller in the overall fraction. All right, so this alternating series converges by alternating series test. All right, now we check about conditional or absolute. So let's take a look at the series from 2 to infinity of just n over n cubed minus 5. I wouldn't use integral test for this because u sub's going to fail. These are more than a degree apart. So you definitely need a comparison test here. So we're comparing n over n cubed minus 5 to n over n cubed, which I understand is 1 over n squared. But comparison-wise, it's easier to say this first fraction is bigger because it's got a smaller denominator, meaning like 1/2 is bigger than 1/4, for example. And then what do we know? We know that the series from 2 to infinity of 1 over n squared, I'll use the simplified version, is a convergent p-series. So yet again, I guess I haven't come to my conclusion. So let's see. The one on the bottom is converging, which means we need to do LCT to make our conclusion. The limit as n approaches infinity of our unknown divided by our known, I'm going to say times n squared over 1. That comes out to 1, n cubed over n cubed. So these two series act together. That means that our positive series from 2 to infinity, n over n cubed minus 5, it also converges, and that's by the limit comparison test. So we're back to converge. So the original series in question, the alternating one, converges absolutely. Okay, final question. Same thing. So this series is alternating. The limit as n approaches infinity of 1 over square root of n plus 4 is equal to 0. It's reasonable to say if I plug n plus 1 in, that square root of n plus 5 on the bottom will make a smaller fraction than square root of n plus 4 on the bottom. So this series writing it all out, converges by alternating series test. All right, so let's take a look at the positive series. 1 over square root of n plus 4. Again, you could do integral test, but why do that when you can also just do a comparison test? Why integrate if we don't have to? Compare 1 over the square root of n plus 4 to 1 over the square root of n. The first fraction is smaller. We know about the series from 0 to infinity of, I guess it wouldn't be 0, but whatever. So 1 over square root of n. We know that the one from 1 to infinity is a divergent p-series. I don't think we have to adjust for that, but I'm not 100%. I could say 1 right there. The one term isn't going to make a difference. And then I need to use LCT again because the one on top is diverging, and that's not affecting the one that's growing faster. So the limit as n approaches infinity of 1 over radical n plus 4 divided by 1 over radical n, or times radical n over 1, that's equal to 1. So these two series act the same. It means that this positive series of 1 over radical n plus 4 also diverges by limit comparison test. So because the alternating converges but the non-alternating diverges, the original series still converges, but it converges conditionally. And remember, converges conditionally just means this thing will converge on the condition that it is alternating. It just means that it doesn't converge all the time. It has to be alternating for that to work. All right, that finishes this video. come into office hours if you have any questions or want more practice with this.